Professor Nikolai Vasilevski from Simestab 2 in Mexico City with the talk Polyanalytic Function Spaces. Please. Professor Vasilevski. Could you start, please?
Mute. Yeah. Is it okay now? Can you hear me?
Sí.
Okay. Okay. So, well, first I met, or we met with Enrique Ramirez de Arellano in 1989. It was in Montpellier, France. He came for Strange for Me country, Mexico. I came for Strange for him country, Ukraine. Well, after this meeting in 1992, I was invited with my colleague from Odessa to Mexico City. And I greatly appreciate Enrique's help. I will never forget that, for his enormous help to accommodate me in Mexico City, this strange for me country. It's really very nice, very interesting, and very useful help offered by Enrique. Enrique, if you hear me right now, thank you very much again. So I will speak about polyanalytic function spaces. What's that? It's some kind of closed relative of analytic functions, and they are defined as follows. We have n differentiable function phi in the domain D in complex plane. It is called n polyanalytic or n anti-polyanalytic if it satisfies the powers of the Cauchy-Riemann equation. So for n equal to 1, it's just analytic or anti-analytic function. It is known that these conditions are equivalent to the following representation. N polyanalytic function is just polynomial in Z bar of degree n minus 1 with analytic coefficients. And an anti-polyanalytic function, again, is a polynomial in variable Z with anti-analytic coefficient. They are really have many in common with analytic function, although they have some very different properties. A simple example, function f of z equal 1 minus z bar is both 2 polyanalytic and both 2 anti-polyanalytic. Note that they vanish on the boundary on the unit disk, on the unit circle. It's identically 0. But nevertheless, the function is not 0, which is not the case of analytic function. So in some sense, they're similar. In another sense, they're quite different. Okay, what is this talk about? There are many recently considered weighted L2 space over different domain D on the complex plane. And what we are going to study, we are going to study like Bergman space of analytic function in this spirit. We denote by script an and script a tilde n, the closed subspace in our space, Hilbert space H, which consists of all n polyanalytic or n anti-polyanalytic function. One can introduce as well the so-called true n polyanalytic function. This is the direct difference between n polyanalytic function and n minus 1 polyanalytic function. That is, those functions that satisfy the nth power of Cauchy-Riemann equation, but not nth minus 1, nth minus 2, and so on power. It's the aim of this talk characterize the structure and properties of the above spaces, we would like to characterize them in a way that this description do not depend as much as possible on a particular space H under consideration. So we have generic Hilbert space, weighted L2 space, and we would like characterize the polyanalytic, anti-polyanalytic, true and analytic, true and polyanalytic, true anti-analytic functions in a form, I would say, H independent. First of all, let us introduce the orthogonal projection. Pn would be projection onto an analytic function, Pn tilde orthogonal projection onto an anti-polyanalytic function, P sub n in brackets would be projection from H onto true n polyanalytic function, and P tilde n in brackets projection, orthogonal projection from H onto true n polyanalytic function. Okay, first some history. It was Juraev who first observed strange connection between polyanalytic function and two-dimensional singular integral operators. These are very well-known operators CD and its adjoint CD given by these formulas. What he found that the orthogonal projection Pn and Pn tilde can be expressed in terms of this two-dimensional singular integral operator plus some compact summand, which may vary when the domain D varies. What is interesting that for the case of the unit disk, both compact summands are equal to 0. So we have just a representation in terms of identity operators in product of powers of this two-dimensional singular integral operator. Now, concrete example of description of the space. Let us consider the so-called poly-Bergman space or polyanalytic spaces defined on the upper half plane. In this case, our space H would be just L2 on the upper half plane with the normalized Lebesgue measure. And the result of 99 says that this L2 space on the upper half plane can be mysterically decomposed as a direct sum of all true and analytic functions plus direct sum of all true anti-analytic functions. Moreover, these true analytic and true anti-analytic functions can be moved one to each other using powers of this two-dimensional singular integral operator. Operator S over P to the power K moves through n analytic function to n plus K through analytic function, and move down through anti-analytic function, while his adjoint operator moves down through polyanalytic function and moves up through moves up through anti-analytic function and moves down through analytic function. So again, strict connection between two-dimensional singular integral operator and polyanalytic functions. Moreover, we can describe how true and analytic functions look like. We need to consider analytic function, apply the powers of a singular integral operator, it will have true and analytic function. The same story for true anti-analytic functions. And again, projection can be described in the Juraev style formulas. Each projection, Pn, is identity minus the product of powers of S and S star. This is the story for Poly-Bergman spaces over the upper half plane. In the unit disk, the story is a bit different. In the unit disk, L2 in standard L2 over unit disk can be decomposed as a direct sum as just true and polyanalytic function. Again, we have derived-like formulas which describes orthogonal projections onto this n-analytic and n-analytic function in terms of singular two-dimensional singular integral operator. And these operators move corresponding polyanalytic and anti-polyanalytic functions, but modulo one-dimensional subspace. Here you see one-dimensional subspace appear. You need to subtract this one-dimensional subspace from the corresponding spaces. Now, poly-Fock spaces. Let us consider L2 space over the complex plane with a standard Gaussian measure. Then, this L2 space can be decomposed, as a direct sum of the true and analytic subspaces. And we have again certain operator which moves up and down true and polyanalytic spaces. This is a strange operator, A dagger and A. They are mutually enjoyed, densely defined in L2 with Gaussian measure, and are given by this formula. A is just derivative with respect to Z bar, and A dagger is a combination of multiplication by Z bar and derivative with respect to Z. As a corollary, we have that weighted powers of the operator A dagger gives an isometric isomorphism between the Fock space of analytic function onto n true and analytic function space. Something wrong? Okay. And we can give an explicit formula for any true and analytic function. It is uniquely defined by a certain analytic function and have this explicit form. It's a sum of combination. Well, it should be, as we know, it should be polynomial with respect to Z bar with analytic coefficient. But analytic coefficient is always derivative of the same analytic function. So each analytic function is uniquely defined true and polyanalytic function. And this is isomorphic isomorphism. They have the same powers. Now, this is the result of very neurally appear paper when we revised or look in another form onto polyanalytic poly-Fock spaces. The first very important observation that our operator A and A dagger, which we already know, they are mutually enjoined and densely defined in a L2 space over C with Gaussian measure. They obey very nice commutation property. They commute up to identity. And what is important for us, that the kernel of the operator A, let me recall this is just derivative with respect to Z bar, is infinite dimensional. Let us think first of situation where we have two operators, A and B, which commute to identity. Let me recall in this connection classical Fock space formalism. What's that? Let us consider three-dimensional Heisenberg algebra H3, which is generated by three generators, A, B, and 1, obeying this commutation relation. Having that, the Fock space formal construction is given by the representation of the Heisenberg algebra on a separate Hilbert space H, so that this operator, images of A, B acting in H, satisfy the above commutation relation. Second, there is a normalized element. Physicists like to call them ket or phi naught. This element of H has norm 1. It's called a vacuum vector. It is annihilated by the operator A. And the third very important condition is that the span, linear span of all elements of powers being applied to this vacuum vector is dense in H. So what do we have? We have a representation of the Heisenberg algebra on the inseparable Hilbert space satisfying to these three conditions. One can call this Hilbert space constructed as the Fock space related to the operator A and B. Classical examples. H is L2 over R. A is this operator 1 over square root of 2 x plus derivative d over dx. B now is a dagger adjoint to B 1 over square root of 2 x minus derivative with respect to x. The very well known lowering and raising operators in quantum theory, and the vacuum vector is nothing but the ground state of the harmonic oscillator. Another well-known example constructed by Berezin, the space H is a Hilbert space of all anti-analytic functions endowed with the following scalar product. The operator A is the derivative with respect to z. Operator B is again a dagger. Adjoint to A is multiplication by z bar. Oh, sorry, I would say A should be derivative with respect to z, and a dagger multiplication by z. And the vacuum vector function phi naught is equal to 1. In our particular case, related to the Fock space, we have infinite dimensional kernel of operator A. So we would like to extend our Fock space formalism to the case when the kernel of A is not one-dimensional, but again A and B commute up to identity, and now we assume that the linear span of all spaces, powers of operator B applying to the kernel of operator A, is dense in H. The classical case corresponds to the case when L1 is just one-dimensional and is generated by the vacuum vector. In the situation of multidimensional kernel of operator A, we can define K poly A space HK as the closure of all elements that satisfies to the equation power of operator case power of operator A applied to I H is equal. That is kernel of operator A to the power K. One can easily verify this commutation relation. It implies that taking each A1 from the kernel of operator A, the element HK, its b k minus 1 power belongs to k Pauli space. And this k Pauli space, Hk, in fact, is the closure of the linear span, linear sum of L1, L2, and so forth, Lk. What is interesting here? Based on operator A and B, we can consider three generically unbounded, densely defined operators, Jk plus, Jk naught, and Jk minus, defined by this formula. This operator for arbitrary k obey SL2 algebra commutation relation. This is very well known commutation relation of SL2 algebra. And one can detect that for natural numbers k, the space Vk we just introduced, linear sum of L1, L2, and up to Lk, is invariant under the action of this operator Jk plus minus and Jk 0. So our k Pauli alpha space Hk can be defined alternatively as the closure of the maximal by inclusion invariant subspace for the action of the operator Jk plus minus Jk 0 obeying SL2 algebra commutation relation. So very interesting and quite unexpected relation between k Pauli spaces and representation spaces for LS2 algebra. A particular case, as we saw an example, when the operator B is adjoint to A, so when B is a dagger, gives much more interesting and important properties. First of all, if B is adjoint to a dagger, then the different spaces Lm are orthogonal among each other, and the weighted raising operator a dagger restricted to closure of Lk minus 1, move it isometrically to the closure of next Lk, so it raises it up to one place. And weighted lowering operator A is isometric isomorphism between the closure of Lk and closure of Lk minus 1. Now we can define a part of k Pauli spaces, true k Pauli spaces, again in the same manner. It just would be direct difference between space Hk and Hk minus 1. What is interesting here that now, because of this orthogonality given by proposition, it would be just the closure of k minus 1 power of the initial space L1. And the true k spaces is just the direct sum of all true k spaces from L equal to 1 to k, where each true L spaces is the L minus 1 power of operator D a dagger applied to the closure of the kernel of the operator A. As a corollary, we see that all true k spaces are isomorphically asymmetric between each other, and the weighted power of the operator A dagger gives the isometric isomorphism of the initial space H1 to the space true space HK. And its inverse isomorphism is given by the weighted powers of the lowering operator A. And the space H is direct sum of all true K spaces. What is interesting here? We do not assume any analytic properties of the spaces HK, HK in the brackets. What we need and what we use actually is only that A and A dagger are mutually joined. They commute by identity, and the linear space of all powers of A dagger applied to the kernel operator A is dense in our Hilbert space. All these axioms, in fact, imply the particular properties of true K spaces, poly K spaces, and decomposition of the initial space H on the direct sum of true K alpha spaces. So the situation which we saw in polyfoc spaces, in fact, is a particular case in a general abstract procedure related to extended formal construction of the Fock space. So we may apply now what we have seen in this abstract contraction to the particular situation of the polyfoc space when the operator A is just partial derivative with respect to Z bar, and operator A dagger is multiplication by Z bar minus derivative by Z. They, as we know, mutually compute, obey corresponding commutation relation. Kernel of the operator A is infinite. And what's that now? Polyfoc space AN is just this sum of powers of operator A dagger applied to the initial Fock space of analytic functions. And true polyfoc space A n in bracket is just n minus 1 power of the operator A dagger applied to this Fock space of analytic function. Moreover, if we introduce again operator J k plus minus, J k naught for natural number k, this operator will obey SL2 algebra commutation relation, and they are bounded in each polyfoc space AN. And again, polyfoc spaces of analytic function can be defined alternatively as a maximal by inclusion invariant subspaces for the action of our operators obeying SL2 algebra commutation relation. So in some sense, we unhide the Lie algebraic characterization of our favorite polyfoc spaces. There is an interesting connection between polyfoc spaces and some physical problem, which is called Landau magnetic Hamiltonian. Let us consider operator delta tilde, which in fact Laplacian partial derivative of second order with respect to Z is Z bar minus Z bar times the partial derivative with respect to Z bar. I should say here some magic physical word. This operator in suitable units and up to additive constant is a realization of on L2 over C with Gaussian measure of the similarly transformed Schrödinger operator describing the transverse motion of the charged particle involving in the complex planes subject to a normal uniform constant magnetic field in the asymmetric Landau gauge. Well, anyway, this operator turns out to be just a product of a dagger times A. And applying the properties of A dagger and A, we see that a restriction of this operator delta tilde onto the each true K polyfoc space is nothing but the scalar multiplication of the identity operator. This immediately implies that the spectrum of the operator L tilde consists of infinitely many equidistant eigenvalues K minus 1, each of infinite multiplicity, called in physics Landau level, lambda K is K minus 1, and the corresponding eigenspaces is nothing but the true K polyfoc spaces. This is a very interesting application of the true K polyfoc spaces related to the famous Landau magnetic Hamiltonian. Now let us turn to our initial setting. We consider a domain D being either unit disk or complex plane, and denoted by J is either unit interval or L plus, so that in all the time D would be J times unit circle. There are many weighted Gilbert, non-standard weighted Gilbert spaces recently considered. Weight is a probability measure which depends only on radial part of Z. And we assume that the measure is so that the linear span, of all monomials, powers of Z times powers of Z bar is dense in our space H. What we have already considered, Poly-Bergman spaces when we have a unit disk and weight is just 1. Polyfoc spaces when the domain D is C and the weight is Gaussian measure. We have a very known standard weights. For the unit disk is the powers of 1 minus model Z square in the powers lambda. Lambda is greater than -1. This very standard weight in the Bergman space theory. And weighted Fock measure, weighted Gaussian measure when positive parameter alpha is involved. Several examples of recently considered non-standard weights. For the unit disk is standard combined with some exponent, and the complex plane C, for example, this measure with corresponding parameter, and this measure with corresponding parameter. This is just a few examples. There are many, many spaces with different radial measure have been considered recently. Okay, we know that monomials are dense in H, and let us consider scalar product of two different monomials. Easy calculation showed that this product is multiple of delta function of difference P minus Q, K minus L times this integral over our set J. So it is easily seen that these monomials are orthogonal if and only if the difference between powers Z and Z bar is the same. But they are not always orthogonal. And the next step is to construct the orthogonal base in our space H. So we fix the models of the difference between powers and introduce the space L2 over J with this weighted measure, d nu psi of S. Then, by the classical theory of orthogonal polynomials, there exists a sequence of orthonormal polynomials in the space L2 over J that satisfy to this property. And these orthonormal polynomials give a basis in our L2 space. Based on these orthogonal polynomials, the proposition said that the collection of functions is the orthonormal basis in our Hilbert space H. So if you would like to construct the orthonormal base in our Hilbert space H, what we need to do, we need to use the series of orthogonal polynomials and construct the set of orthogonal polynomials. In the classical case of the unit disk non-normalized using this, these orthonormal polynomials P is nothing but shifted Jacobi polynomials. In the case of the standard Gaussian measure in the space C, these polynomials are nothing but the classical Laguerre polynomials. But for different weights, we need to construct by hand orthogonal polynomials. And I will give just one example. Let us consider space C, L2, with this strange measure, e to the minus power of modulus z, not 2, but 4. So there are no classical orthogonal polynomial related to this measure. So we need to construct them by hand using either a general formula for orthogonal polynomial or 3-term recursive formula. I did this and constructed. This is just example of the few initial basis element for this strange space. Well, in this, our generic Hilbert space H, we introduce the operator S. This operator S acts on the basis element in this space as follows. S moves E PQ to the E P minus 1 P Q plus 1. This is a partial isometry. Its kernel is the space of all anti-analytic functions, and the orthogonal complement to the image is the space of all analytic functions. It's a joint operator, again, a partial isometry, whose kernel is the space of analytic function, and complement, orthogonal complement of the image is the space of all anti-analytic functions. Moreover, these products are orthogonal projection onto the corresponding spaces. It's very transparent to see the action of this operator in this picture. We consider the grid when we identify each basis element PQ with the node having coordinate P and Q. What in this picture the operator S does? It moves its nodes PQ to the nearest northwest node. And the operator S star moves each node PQ to the nearest southeast node. So the very nice and very simple graphical interpretation of the action of the operator S and the star on the basis element in our space H. Well, we can decompose our space H onto the direct sum, infinite direct sum on the finite dimensional space HK. HK is the linear span of all basis elements such that P plus Q is equal to K. Now, let us formulate the properties of our operator S and S star. First of all, derive Likes formula. Orthogonal projections are related, are given in terms of identity minus product of S star or S star S, and each subspace HK in this direct sum decomposition is invariant under the action of operator S and A star, and the restriction of this operator are nilpotent. Corresponding powers are equal to 0. Now, very interesting example. If you consider particular case of H is L2 over the unit disk, then the operator, our abstract operator S and R star, is nothing but that our favorite two-dimensional singular operator SD and S star D introduced by Derive. And the properties of operator S and S star permit us and hide very unpredictable properties of this two-dimensional singular integral operator. First of all, if we decompose L2 over the unit disk is the corresponding direct sum of finite dimensional subspaces, that these finite dimensional subspaces are invariant under the action of operator SD star. So this two-dimensional singular integral operator possesses infinite collection of invariant finite dimensional invariant subspaces. And moreover, the restriction of this operator on these finite dimensional spaces are nilpotent. Okay, let's go back to the generic operator S star for generic our space H. We have that these products applied to any element F and H is the same element H modulo some element from an analytic function. This product is identity modulo an element of an anti-analytic function. Powers Fn powers F of S star as the powers of partial isometries are also partial isometries with corresponding kernels and images, and corresponding orthogonal projection onto the orthogonal complement of images are given by this formula, which implies the following coordinate description of an analytic function is the kernel of the power of operator S star, n anti-analytic function is the kernel of operator S, is the span of this element of basis, and all the time we have the exact analogous of the Derive formula. But in this case, this is not anymore two-dimensional singular integral operator, but operator S and S star we introduce. We may introduce two other partial isometries, V and V tilde. What V tilde does? It moves EPK to EPK plus 1. So in our grid, it moves just one node north, and V tilde move just one node east. These isometries are connected with isometries S and S star in the following way. Now let us pass to true polyanalytic in true anti-polyanalytic spaces. Again, in our generic Hilbert space H. This is just, we have already defined what's the true and analytic and true and anti-analytic. Basis-oriented description, after all, of true and analytic and true and analytic function is follows. It's just the linear span of L of all element of basis when the Q is fixed. And true and anti-analytic is the linear space of basis element when the parameter P fixed. And again, our partial isometry says that all true analytic and true all anti-analytic functions are isomorphic, isometric among each other. And our partial isometries, V and V tilde, give corresponding isomorphism with the initial space of analytic and anti-analytic function. Okay, as an example, we can consider again L2 over the unit disk with standard L2 over the unit disk, and this isometries which moves different true polyanalytic in true anti-polyanalytic spaces is given in terms of two-dimensional singular integral operator combined with our isometries V and V tilde. But anyway, for each our generic space H, it is a direct sum either of all true and analytic or direct sum of all true anti-analytic functions. We see some analogy of the previously considered polyfoc space when we have direct sum, when we have that all L2 spaces direct sum of true polyfoc spaces, and there were involved some lowering and raising operator A and A dagger. So the question is, was it particular case of Fock space, or this is a generic situation? And it's generic situation. Let us consider the following proposition. Let H be any separable infinite dimensional Gilbert space. Then the following statements are equivalent. First, the Gilbert space H admits a direct sum decomposition of its subspaces, all having the same finite on infinite dimension. Second, there are mutually adjoint unbounded operator A and A dagger having common domain dense in H, such they obey our favorite commutation relation, and the union of all spaces Ln powers of A dagger of the kernel of operator A is dense in H. So in fact, this generic situation where the orthogonal decomposition onto the subspaces of the same dimension is equivalent to the existence of operator A and A dagger with the desired commutation relation. Moreover, in this abstract situation, this abstract true spaces are either of the kernels of the operator A to the power k, or the image of the powers of A dagger of the kernel of the operator A. Now we can construct operator A and A dagger for our space space H. It is given in the it is given by the following action of the basis element of our space H. They satisfy corresponding commutation relation, and it's their weighted powers exactly act as isomorphic. Isomorphism raising or lowering true polyanalytic or true anti-polyanalytic spaces. What is interesting, then we can construct all the bases starting from the very first element E00. As our measure was probability, E00 is just identically 1. So each basis element is the following weighted powers of element A dagger, L tilde dagger. And we can construct reproducing kernel for each true and analytic space, starting from the reproducing kernel of the analytic space A. This is the formula. As an example, we may consider L2 over C with weighted Gaussian measure. Now the operator A dagger and A tilde dagger admits a very nice form in terms of differential operator. They obey necessary commutation relation. This permits us immediately recover orthonormal basis in this weighted Gaussian measure space. Permit us describe n true and polyanalytic Fock space in this case, and permit us easily recover reproducing kernel for n polyanalytic space, which is given in terms of kernel space for analytic functions time Laguerre polynomial applied to this case. Well, probably my time is over, so I probably stop here. Thank you very much.
Thank you very much, Professor Vasilevski. Okay, so now some questions, comments, please, remarks.
So, about the reproducing the reproducing kernel, is this similar to Cauchy's integral formula?
No, not at well. It's reproducing kernel. What's that? Integral operator with this kernel is just a projection of any L2 function onto the corresponding subspace.
So, but then do you have some kind of Cauchy integral formula to reproduce the form with some integral on the boundary?
Well, not exactly, because say for Fock space or Fock space with weighted measure, it is this analytic space is just the space of entire function. So no boundary values at infinity. So it's just impossible.
Okay, thank you.
Thank you. Okay, more questions?
Can I make, is it possible to extend this theory to higher dimensions, to the domains in Cn?
Well, you know, it is easy to define, say, polyanalytic space as the kernel of powers of Cauchy-Riemann operator with respect to each variable. The problem is how to describe them in some reasonable term. And the question is, what is the notion of true polyanalytic spaces? In the one-dimensional case, the n polyanalytic space form a flag of growing spaces. But so it's ordered situation. In the higher dimension, it's just partial order. There is no, say, complete order. We did something in this direction with Turbiner in this recent paper for multidimensional Fock space. The nice properties of multidimensional Fock space is this a tensor product of one-dimensional Fock space. And then we define polyfock spaces and true polyfock spaces, again, like an representation spaces for the action of certain Lie algebras. Because in that case, there are no common accepted notion. What does it mean, n polyfock space? Because we can rearrange true n spaces in many, many different forms. So we suggested a natural definition of n polyfock spaces in various dimensions in terms of representation spaces for certain Lie algebra representations.
Okay.
Sounds nice.
Can I make some comments?
Sure.
Yes.
First of all, let me say, I have 3 comments. The first one is about representation theory for SL2. As we know that for semi-simple Lie algebras, there are infinite dimensional representations, finite dimensional representations. Infinite dimensional representations, it's not very well defined and very well developed subject. And we, with Nikolai, presented an example of SL2, the theory, particular theory of infinite dimensional representations. Second of all, let me mention that this remarkable measure, what Nikolai demonstrated on page 21, this exponential minus modulo z to the 4, has extremely important and mysterious importance, I would say, in physics. And I call really, if possible, to study these spaces with such measures. And the third question, it's about what Quiroga mentioned. From physics point of view, the most important case, it's the polyanalytic functions on C2. So once we have corresponding Hilbert space with a Gaussian measure, but on C2. And we only started with Nikolai to develop this for the case of algebra SL3. For SL3, one can write a similar representation as was presented for SL2. And there are miraculously interesting results coming for this SL3 related polyanalytic function. Thank you.
Okay. One more question. We have just 2 minutes for the next talk. Okay, if that is the case, thank you very much, Professor Vasilevski.
Thank you.
In 2 minutes, we continue with the talk